Hello and welcome to Mike Academy. So in today's class, we are going to be looking at partial derivatives. We focus on introduction of partial derivatives and majorly on first principle method of differentiating functions partially. Now, partial derivative is simply a term used when differentiating a function of more than one variable. For instance, let's say I have z to be equal to x and y multiplying one another, and I am asked to differentiate z with respect to x. So this symbol is symbol for partial. So I'm asked to partially differentiate z with respect to x. That simply means that I should treat y as a constant and differentiate z only with respect to x. Now, this is a good example of what a function of several variables is. I have c to be equal to x and y. This simply means that if x is equal to, let's say, 2, and y is equal to, let's say, 3, then z has a value. This simply means that z is equal to, if x is 2 times y is 3, and this simply implies that z is equal to what? 6. So which means z depends on the values of both x and y to be defined. That makes z a function of x and y. So mathematically, you can simply say that z is a function of x and y, which means z depends on the value of x and the value of y to be defined. So this is what a function of more than one variable or a function of multivariable is. When you have a function depending on more than one variable, then that is simply a multivariable function. Now, if you're asked to differentiate z partially with respect to x, in that case, you're treating y as a constant and you're simply saying z only changes with respect to x. So all the theorems and ideas you know when differentiating the normal derivative and constants together also play. For instance, if I have y to be equal to 2x, we simply say that the y all over the x is equal to what? 2, simply because x here is to the power of 1. And if I differentiate x, I will simply have 1. Use that 1 to multiply 2. The value remains 2. Similarly, if I have y to be equal to just 2, we simply say the y all over the x is equal to what? 0. Because 2 is a constant and 2 does not contain any variable x attached to it. So the derivative of a constant always remains 0. The same thing happens if I have z to be equal to xy and I'm asked to differentiate. Okay, let's see if I have z to be equal to just y and I am asked to partially differentiate z with respect to x. This is going to be what? 0, because there's no x attached to y. Z is only with respect to y, which means z is supposed to change with respect to y. So if I'm asked to differentiate z with respect to x, then it simply means that this is going to be 0, because in this case now I will be seeing y as a constant. So that's the idea behind partial derivative. Differentiating a function with respect to one of the variables while keeping the other variable as a constant. That is the idea behind partial derivatives. Now, having this in mind, let us try to solve this problem from first principle. This video is targeted to explain the first principle method of partial derivatives. Okay, so let's begin. Let's say we are given, of course, z to be equal to x and y, and we need to find the partial derivative of z with respect to x. Now, what you do is, since z is changing with respect to x, then you increase z by a change in z. That simply means you're also going to increase x by a change in x, keeping y as a constant, since I am asked to find partial z, partial x. So if I increase z by a change in z, so z plus change in z, this is going to be equal to increase x by a change in x, then you hold y as a constant. So this is the first principle method. Okay, so you have z plus change in z, and this is equal to, now the next thing is to expand the bracket using y. Y times x gives us xy plus y times change in x gives us y change in x, and you simply have this. Now at this point, the next thing to do is transfer z over to this side of the equation. Now, if you do that, you're left now changing z on this side of the equation. So you have change in z to now be equal to, put down everything you have here, xy plus y change in x. Remember, this is positive z, and if a positive sign cross an equal to sign, automatically it becomes negative. So I have minus z. But not forgetting, recall that earlier we said z is equal to xy. This was a question. So in place of z, put in the original value as xy. You're going to have change in z is equal to xy plus y change in x minus, in place of z, the value becomes what? X and y. So you simply have this. Now, let's rearrange this equation a little bit. We simply have change in z to be equal to xy. Now bring minus xy closer, minus xy plus y change in x. So observe that xy cancels xy because you have xy minus xy, that's off. So this simply implies that change in z becomes, now I'm left with y change in x. But we are asked to find partial z all over partial x, which means at this point what you do is divide both sides. Okay, divide both sides by change in x, and you simply have change in z all over change in x, and that's equal to y change in x all over change in x. So observe that change in x strikes change in x. This simply implies that change in z all over change in x automatically becomes what? Y. So since I have change in z over change in x to be y, observe now that there is no other term attached to y, no other variable in x or change in x attached to y. So automatically this becomes, this simply implies that partial derivative of z with respect to only x gives you what? The value as y. So the value or the answer to that question is simply y. Now, at the end of every video or at the end of every example solved, I'm going to be showing you a shortcut. I'm going to be showing you a shortcut on how to carry out these partial derivatives without solving from first principle. So you can do this first of all, know the answer before going through first principle approach to confirm your answer. Okay, so I'm going to be showing us a shortcut approach to solving this before we pick the next example on first principle partial derivatives. Okay, so before we proceed, now let's consider back the question. We have z is equal to x multiplying y, and we need to differentiate this partially with respect to x. So I'm going to be showing you a shortcut. Now, before going to the shortcut, let's observe if we have y to be equal to x squared, and we are asked to find dy dx, we say dy dx is equal to what? We use the power of x to multiply x, so it becomes 2 times x to the power of 2, then subtract 1 from the power. So this simply means that dy all over the x is equal to what? I have 2 times x gives us x, 2 minus 1 over here, and the power becomes 1. So this is actually what? 2x as dy x. So the same thing applies here. I have z to be equal to xy. This simply implies that z is equal to x to the power of 1 times y to the power of 1, because x to the power of 1 still remains x, y to the power of 1 still remains y. Now, I want to differentiate z with respect to only x, that is a partial derivative. In that case, I say you hold y as a constant. Now, let's apply the principle of differentiation to x. Remember, use the power of x to multiply x. The power of x here is 1, so it becomes 1 times x to the power of 1. Then subtract 1 from the power, it becomes minus 1. You have this. Alright, so partial z all over partial x is now equal to, so I have y into 1 times x, of course, is x. At the power here, 1 minus 1 is what? 0. So you have this. So this is actually equal to y into x to the power of 0 is 1. So I have 1 times y. So this simply implies that the partial derivative of z with respect to only x is simply what? Y. So this is the shortcut approach to solving that same problem which you use the first principle method to. Alright, so let's consider another question to explain the first principle method of partial derivatives. Alright, so let's say we are asked to find partial z partial y given this function z equals x squared y plus xy squared. Now we have to do this as well from first principle. So the first thing you observe now is that in this case, z is changing with respect to y, which means I'm going to be holding x as a constant. So let's do this and see. Remember, if I increase z by a change, then in this case now, I'm going to be increasing y by a change. So I have z plus change in z. That simply becomes hold x as a constant. So x squared is held as a constant. Open a bracket, increase y by change. So I have y plus change in y. Okay, plus now you hold x also as a constant, increase y by a change. So I have y plus change in y, but not forgetting that this is y squared. So since y is squared, it means this increment will also be what? Squared. So I have this. Now, before proceeding, let us first of all get this expansion, okay? Then substitute back into this equation. So let's simply call this equation 1. Then let's get this expansion separately and substitute into equation 1. We need to expand y plus change in y all squared. This is simple as saying y plus change in y, okay, multiplying y plus change in y. Now you can as well use the Pascal's triangle to expand this Pascal's triangle for second power to expand this. But let's just go through the normal expansion procedure. Okay, so I have that y plus change in y is now equal to, so I'll be using every term in this bracket to expand every term in this bracket. So beginning from y, I will use y to expand this whole bracket, y plus change in y, okay, plus next I will use change in y to expand this whole bracket, change in y multiplying y plus change in y. I will simply have this. Okay, so y plus change in y all squared, not forgetting all squared, is now equal to, so let's obtain now y times y here gives us y squared plus y times change in y here gives us y change in y plus similarly change in y times y over here gives us y change in y plus change in y times change in y gives us change in y all squared. Okay, so y plus change in y all squared is now equal to, this is y squared plus, I have y change in y plus y change in y, that gives us 2y change in y plus change in y all squared. So this expansion is actually this. So in place of equation 1, we are going to be plugging in place of x plus, in place of y plus change in y squared in equation 1, we're going to be putting these whole values down there. All right. So not forgetting, equation 1 we had z plus change in z to be equal to x squared into y plus change in y plus x into y plus change in y all squared. So in place of y plus change in y squared, let's put in the real expansion. So I have z plus change in z to be equal to x squared into y plus change in y plus x into, in place of this, we simply put y squared plus plus 2y change in y plus change in y all squared. Alright, so at this point, let's now expand the bracket using x squared and using x over here. So we have z plus change in z to be equal to x squared multiplies y gives us x squared y plus x squared multiplies change in y gives us x squared change in y plus x multiplies y squared gives us x y squared plus x multiplies 2y change in y, that gives us 2xy change in y plus x multiplies change in y squared, that simply gives us x change in y all squared. We have this. Okay, now having expanded, the next thing to do is transfer z over to this side of the equation. So if you send z over to this side of the equation, you're going to have change in z left over here, and change in z becomes, put down everything, you have x squared y plus x squared change in y plus xy squared plus 2xy change in y plus x change in y squared. If z crosses over, it becomes minus z. Now, I'm not forgetting, okay, but z itself is actually equal to, we said z is equal to x squared y plus xy squared. Okay, this is our value for z. So all we need to do at this juncture is, wherever we see z in the equation, especially in this equation, put in the value of z. All right, so if we do that, we are going to be having change in z to be equal to, we have here x squared y plus x squared change in y plus xy squared plus 2xy change in y plus x change in y squared minus, in place of z, the value of z remains x squared y plus xy squared. So you have this. Okay, so next thing now, we expand this bracket using negative sign. We are going to have change in z to be equal to, this gives us x squared y plus x squared change in y plus I have x y squared plus 2xy change in y. Okay, plus we have x y x change in y squared. Okay, so if minus multiplies here, we have minus x squared y. Similarly, minus multiplies xy squared gives us minus xy squared, and we have this. Alright, so at this point, we can either rearrange. Let's collect like terms together. I have x squared y here. I have minus x squared y. So these two can strike. X squared y can cancel, minus x squared y. Again, I have over here, I have xy squared here, and I have minus xy squared here. So these two can as well strike. Xy squared cancels, minus xy squared. So let's put out what we have left now. Alright guys, so please just pay attention to everything we have left here. Over here I have change in z, and here I have x squared change in y. I also have here 2xy change in y, and I also have x change in y squared. So these are the terms left, so just take note of it because we are flipping the page now. Alright guys, so after cancelling out, we simply have change in z to be equal to, these are all we have left. Now at this point, the next thing to do is to divide both sides, or divide all through. Okay, divide all through by change in y, and if we do that, we are going to have change in z all over change in y to be equal to x squared change in y over change in y plus 2xy change in y over change in y plus x change in y squared all over change in y. We simply have this. So from here, I still have change in z divides change in y, and this is equal to, over here, change in y strikes change in y, so I'm left with x squared plus, similarly, change in y here also strikes change in y, so I'm left with 2xy. Okay, plus over here change in y strikes one of this, so I have x change in y. Now in a situation like this where I still have change in y left on the other side of the equation, the next thing to do is to approach, or take the limit approach. Now the limit approach is simply this, that the limit as change in y approaches 0, the function change in z all over change in y automatically becomes a partial derivative of z with respect to y. Whenever you encounter such situation that after differentiating, you're still having a change left on the other side of the equation, you simply take the limit of that variable. So which means wherever you see change in y, put in the value as what? 0. And if that happens, then this automatically becomes a partial derivative. Now this simply implies that the partial derivative of z with respect to y is now equal to, I have x squared plus 2xy, okay, plus x into, in place of changing y, the value becomes 0. So this simply implies that the partial derivative of z with respect to y is equal to, I simply have x squared plus 2xy. X times 0 is 0, so this becomes the answer to that derivative. Alright, so that's it on first principle. Now, just like I said, at the end of each of these examples, I will show you a shortcut. So with the shortcut, you're able to know the answer before carrying out your first principle differentiation. Alright, so let's try with the shortcut now and see. Let's try with the shortcut now and see. I have that z is equal to x squared y plus xy squared, and I'm asked to find the partial derivative of z with respect to x. Alright, so partial z all over partial, with respect to y, this with respect to y, partial z divides partial y is now equal to, so remember the principle, since I am differentiating with respect to y, it means I am going to be holding x as a constant. So hold x squared over here as a constant. Let's differentiate y. Y is to the power of 1 here. Use the power to multiply y, so I have 1 times y to the power of 1. Then subtract 1 from the power, so you have minus 1. Okay, so that's it for this first derivative. plus on this other side, also keep x as a constant. Let's differentiate y. Y is to the power of 2. Remember, use the power 2 to multiply y to the power of 2. Then subtract 1 from the power, so you have -1. And you simply have this, okay? So partial z all over partial y is now equal to, okay, I have x squared into y. 1 times y gives us y. Then over the power, 1 minus 1 equals 0. So I have y to the power of 0. Plus here I have x into, here 2 times y gives us 2y. Then over the power, 2 minus 1 gives us 1. And I simply have this. And this is equal to x squared, okay, into y to the power of 0 is 1. So keep it aside as 1, plus I have x into 2y, because y to the power of 1 remains 2y. Alright, so after evaluation, this simply implies a partial derivative of z with respect to y is equal to, now x squared times 1 gives us x squared, plus 2y times x gives us 2xy. And this is the same result as what we obtained earlier when we differentiated this function. Okay, as can be seen here, same result as what we obtained when we differentiated this function. So that's how we differentiate functions of more than one variable from first principle, and that's also the shortcut approach to it. Alright guys, so that's it on first principle method of partial derivatives. In the next video, we are going to be looking into product rule of partial derivatives. Please guys, if you're new to the channel, do well to like, comment, and of course share the video to your friend, and do well to as well subscribe to the channel to keep getting updates when content as this drop. I will see you in the next video. Thanks.